So that's how you increase the voltage. So in this diagram, two batteries, each 6 voltage, and each has capacity 10 ampere hour. So the voltage will be 12. But what about the amp? The amp the same. Why? Because they are connected in series. So you do not increase the capacity of the amp of the battery. But you increase in this connection, you only increase the voltage. So if you need more voltage and you don't care about the amp, the same, connect the batteries or the voltage source in series. If you connect the two batteries in parallel, how you connect in parallel? You connect in parallel, positive and positive, they are connected in one point. Negative and negative, they are connected by another point. In this case, they are parallel, so the voltage stay the same. So if you have 6 voltage, you connect it in parallel, negative with negative, positive with positive, and you take the two terminals, one positive, one negative, the voltage still the same, stay the same, 6 volts, but the ampere with capacity or the amp capacity increases, will be doubled, they'll be added. Why? Because you have current reduced I, current I is reduced, then we are added, and this joint will have double. If you want to triple, so just you connect 3 batteries in parallel, then you will have the same voltage and the current will be tripled, and so on. So to increase the voltage, connect in series the batteries. To increase the current and keep the voltage the same, connect them in parallel. What about if you want to increase the voltage and the amp? What do you think? What you're going to do? If you want both, you do 6 in parallel. That's right. So let's just look at this example. Here you go. You got, but you got to use more batteries, not just a couple of them. Like I'm using the same batteries, 6 voltage. So what you have here, I have 6 voltage. So I connect each 6 voltage in parallel, like this one, the positive, negative. I connect this in series. So you have 6 voltage here. You have 6 voltage here connected in series. So you got 12 on this side. But the amp is the same in this branch. The second branch, you have 6 voltage, and you have another 6 voltage. You got 12 voltage, and the amp the same I. So the equivalent, you can make equivalent of this circuit. You will have one battery like 12 voltage, and the current I, and you have another group 12 voltage and another I, and then when you connect them, be added at this point. So you get here 2I. So in this case, you double the voltage and you double the current, what you need for batteries. By the way, they do the same thing with solar panels, because solar panels produce DC. See, if they want to get more voltage, you connect the panels, the PV panels in series. And they want to have voltage, more current, you do the same thing. So maybe this battery represents PV panel, solar energy panel. So you need 4 of them and to make this connection. You will see in the lab how you can get the voltage source. I'm talking about the DC voltage source. You will see this in the lab, similar to like that. So in this diagram, you will see voltage knob and current knob. The voltage knob you adjusted. You got two buttons here, and this one, like the course change. If you want to change big voltage, like by 1 voltage, 2 voltage, and the other one just to do it like fine tuning, like 1.4, 0.6 to add current. It does not like to produce current. No, it's current limiting, to protect your circuit. What does it mean? If you, for example, if you have circuit and you want to protect it. You don't want the current to exceed 1.5 amp. So you adjust this current button here to 1.5 amp. So if the current in the circuit you are working with will exceed 1.5 amp, it will automatically disconnect the power supply. It will turn it off to protect your circuit. And you got here that where you connect the positive and the negative, other one for the earthing. That's a simple power supply. It's the DC power supply. Sometimes we have DC and AC power supply both, but most in the lab they are DC power supply. That's one example of DC AC power supply to use both, and you'll find like this one has 1 amp, 3 amp. It depends what you're going to use, and the common terminal, that's the we common to the old circuit, and the AC. I'm not going to go through the details. I will, because when we go to the lab this coming Thursday, we'll take it step by step. We are going to work with the board that has the power supply already in the board. Simple one. You will have like 12 voltage, 5 volts, and so on. Excuse me. There is something called function generator. You will see it in the lab. Let's just look at this function generator. And we are going also to use it in the lab when we are going to use AC. So function generator give you AC or produce AC signal, but different type of signal, not only sine wave. So when you look at this button here, function, that's where you adjust the function. Do you want to have square wave, sinusoidal wave, sawtooth, triangular wave, whatever the wave that you like to have? This function will help you to choose the waveform type. And this is the range. The range is the frequency, because any AC signal has frequency. What does it mean, frequency? Frequency, it means that how many cycles is a bit every second. You may have high frequency or low frequency. Like, for example, the frequency of the AC supply, we have it here in any building, 60 hertz, right? What does it mean, 60 hertz? When we go to the AC, we'll explain more, but just I'd like you now just to know at least the basic terminology or variables. So when you say the frequency is equal 60 hertz, and in Europe, the frequency is equal to 50 hertz. What does it mean, 60 hertz and 50 hertz? When you look at any AC signal, you will, its sign should be symmetric, the positive equal the negative. That's the positive half and the negative half part. And here we finish one cycle. So as you learned before in physics, C is the period. It means it's going to be repeated. So what is the frequency and what's the period? Period T, the time takes one cycle to be done. One cycle is done, has to finish, one positive and one negative, and then will be repeated again. So that's another positive and negative, and they are equal, another T. So the period is the time that it takes one cycle to finish. And what's frequency? So let's just write T. The period is equal to the time of one cycle. Measure in seconds. Of course, you can use millisecond, microsecond, depends on the length of the period. What is F? It's the frequency. What does it mean, frequency? It's 1 over T. What does it mean? In math, 1 over T, yes, you know, but what does it mean? Hertz, it means cycles per second. It means in 1 second, how many cycles, how many complete cycles are done. So when you say 60 hertz, in 1 second, you can see 50 cycles of those. You see, this is positive, negative is 1 cycle. In 1 second, you will see 60. So if you want to calculate the time of 1 cycle, what you'll do, if you say 60 cycles done
in 1 second. So how many cycles? I mean, 1 cycle, how many seconds it takes? That will be the period, T. Let's just do it. So you will have T, that's T actually, will be equal 1/60. And if we use the calculator, 1/60, 1/60, that will give us fraction, you know, in second, 0.016666 second. Let me just write what we got here. 0.16, and you can repeat it, you know, but just 6 is all the time. Second, if you wanna, so obviously it's very small. The period is really very small. So let me multiply by 1,000 and see how many milliseconds times 1,000. That will give 16. If I round it, 16.7 milliseconds. So it means 1 cycle will take 16.7 milliseconds. That's the period. So here we go back to the function generator. It produces different AC waveforms, and the range, it gives you the range of the frequency. What's the frequency? Now I understand what does it mean. So if you choose 10K, means 10 kilohertz. It means that you want the frequency to be 10,000 hertz. Mean you want 10,000 cycles for 1 second to be done. So you choose them. There are other things, but I'm not going to go to the details, how to adjust the signal, make it up a little bit, down, biased by DC. We'll not talk about, but this is the wave generator used to produce AC signal with small voltage. You can adjust the voltage, magnitude, and usually it's the current that draws is small. So these are the basic type of AC signal in the functional generator that we usually use: sine wave, triangular wave, square wave. And obviously they are symmetric, but using this instrument, you might be able to change to make the positive more than the negative, or the negative more than the positive. That's the function generator. Now let's talk about current. Yes, we mentioned current while we are explaining law. We said 2 amp, 1.5 amp, but what's amp? What does it mean amp? What does it mean current? If you remember the first example we explained to make analogy between the voltage and the tanks full of water, we said that the water will not flow between the two tanks except if the height in one tank is higher than the height of the water in the second tank. Then the water will flow. Current is like the flow of water, but current here is the flow of electrons. And if you remember, we explained last lecture about the free electrons. So we got to have free electrons in the first place so they can move. So we explained last time that these are the free electrons. They are moving randomly, so the resultant is 0. But if you have electric field by connecting battery to this conductor, then we'll have electric field. So the electrons will be aligned together in one direction going toward the positive. So they will have one direction. Once the electrons will flow in one direction from one place to another, that's electric current. So electric current is the flow of electrons. Electrons moving in one direction from place to place. The result does not equal 0. And then we want to define the amp. What is the ampere? We know that the charge, the unit of charge, coulomb, and 1 coulomb is not small amount; it's big amount. You got to have many electrons to make 1 coulomb, because in every electron carry a small amount of charge. So if you have a charge equal to 1 coulomb, and they took 1 second to move from one place to place, that's the 1 amp. So 1 amp is the flow of a charge equal 1. If we have 1 coulomb and moving 1 second, crossing cross-section area in 1 second, that makes 1 amp. Let me explain it in more detail. So if you have a conductor like that, this blue one, and then you got a sheet, and then and this sheet at the cross-section area, and you are observing, you are just looking in 1 second how many electrons will cross this sheet. So let's say that 10 coulombs cross in 1 second. So you say 10 amp. If 10 coulombs cross in 1 second, just look at, and you have the stopwatch, and then you start counting, stop. After 1 second, you found 10 coulomb. So it's 10 amp. So 1 amp, if 1 coulomb cross this sheet in 1 second, that's 1 amp. 2 coulomb cross the sheet in 1 second, that's 2 amp. So that's why the definition I put here, I is the electric current, Q is the total charge, T is the time in second. So that's the charge, total charge in coulomb. T, that's the time in second. I is the current in amp, and we'll call it A. That's the definition of current. So if you want to have 1 amp, 1 coulomb will cross in 1 second. But you got to remember, 1 coulomb is not just a small amount of charge. You got to have many electrons. Electric current is flow of electrons. Flow of electrons has direction. So as I explained previously, that's the way the old textbooks and the used before, that the current coming out of the positive polarity of the current source going through the circuit. That's the direction of the positive current. We call it conventional current. But as we explained before, positive charge do not move because it's heavy. The protons are heavy. What move? Electrons. So that's actually the electron move in this direction, opposite to the positive, but we use this. That's the conventional current direction that we use. Because as we said previously, if the electron move from right to left, that's equivalent to positive charge moving from left to right. But it's not moving, but just as you said, it's equivalent to. So we're using this conventional current direction, always moving according to the positive charge. Example. We have 10 coulomb of charge flow past a given point in a wire in 2 seconds. So it's like that's the conductor here, and you are looking at this point to count, as I said. Then you found that the charge crossing this point, 10 coulomb. Of course, it will be hard to count 1 second. So maybe if you want to calculate the current, you make your stopwatch, for example, 10 seconds, and then you look for how many charge, and you divide the charge by the time, you get there 1 second. So they said that the time, it was 2 seconds, this measurement. So what's the equivalent electric current in amp? So we'll say I is equal Q over T. Q is equal 10 coulomb over 2 seconds. That will give 5 coulomb per second. Coulomb per second means amp. So the current is equal 5 amp. All right. Let's look at this practice. If there are 8 amp of current through the filament of a lamp, how many coulomb of a charge move through the filament in 1.5 seconds? So it's like you have a light bulb here and connected to a power supply. And they said that the current through this lamp is 8 amp. So they want to calculate the charge that moving through this lamp in 1.5 seconds. How many charge should be passed this lamp? So we know that I is equal Q over T. So from this equation, we can say that the charge Q is equal I times time. So the total charge will be equal the current, which is equal to 8 amp times the time 1.5 second. So that will be equal to 12 coulomb, the total charge that passed in 1.5 seconds in this slide. Did you check if the slides of the first lecture was uploaded to the Canvas? You didn't see my Canvas yet? How you are going to measure voltage, current, resistance? You are going, when you go to the lab this week, you are going to use something called digital multimeter, or we call it DMM. Let's have a look at the switch here. Maybe it will be in the lab different. You'll find the off, it will be on the right, but it's all the DMM are the same. Just the arrangement will be a little bit different. So you have here off. That's off when you turn it off. That's important when you go to the lab. You finish your measurement, turn it off to keep the lifetime of the battery, as you know, longer. And then the voltage, you have two options. You can measure AC voltage or DC voltage. AC voltage, you will see it here, the sign of the sign. That means you are going to measure AC voltage. And you have the range, it's 200 and 500. It means 200 voltage magnitude, but frequency, or 500. Up to 200 or up to 500. So it depends on the magnitude of the voltage you are going to measure. Obviously, next lab, we're not going to measure AC, we're going to measure DC. So DC, that will be this one. You'll find like there's a line, straight line, and broken line on the bottom. That's DC voltage. And you have ranges here, start from 200 millivolts. Sometimes we use very small amount of voltage, up to 500 voltage. You change the range, that's the max. For example, if you have voltage, 12 voltage, so which switch you're going to use? 20, that's right. So it's very simple here. Now you go for ohm. Ohm to measure the resistance, and I'm going to explain resistance. Maybe it will take us like 2 lectures to finish it, the resistance. And also, again, that's range. Ohms are measured in, resistance are measured in ohms. And you have range. Start from 200 ohm, then you have 2000, 20K, 200K, 2000K, and so on. And sometimes when you want to check your DMM is working, if you have the two probes, what probe? It's like a wire, and you plug it here. We have 3. Look at this. There's 1, 2, 3 outlet here of the DMM where you put the plug and to measure. So this one, the common, you got to use it when you measure voltage or current. You got to put one wire here, the ground, the common. And then you got 2 choices, the first one or the second one. Most of the time we are using the second one. When you look at the, you can measure amp, voltage, or using the second one. So what about the first one? The first one, we use it in some exceptional cases when you have high current. For example, this one, say 5 amp. In some DMM, it's 10 amp. So in normal cases, we are using number 2. You will see the sign V, ohm, amp. Normal current, depends on the current. If you have high current, then we are going to announce it. The lab says, okay, use this one to measure the when you have high current in the circuit. So these are the where you are going to plug the wire to measure. Well, let's continue here. Here's when you want, if you want to measure voltage, it's different when you measure current. All right. So when you measure current, you got to switch the switch to the current. And we're going to explain how you measure voltage, how you measure current. Because you have the same blocks, you are going to use two, and let's say call it the common, you're going to use these two, but how you connect it in circuit, we're going to explain to measure current and to measure voltage. And if you use the wrong connection in the circuit, that will maybe blew a fuse in the circuit. And most of the time that's happened because when we're measuring current and voltage, sometimes we mix, when we get busy, we mix between the two connections and blew some fuse. So that's to measure the current. And you have other things here. I'm not going to talk about it. That's when you start study semiconductor diodes or transistor. This is something that you don't worry about it right now. But this is the basic things that you should know about DMM. Now let's see how we're going to measure voltage, because in the lab, as far as they are going to measure voltage. To measure voltage, this is the common. You connect one to the common. And this one, that where you will see V, M, measure everything. That was number 2. And let's say that you have a battery or voltage source. So you connect the red one or this one that has V, ohm, amp to the positive. And the common, you connect it to the negative. And you make sure that you adjust this DMM on the DC voltage, because we are going to measure DC voltage of a battery. And then it will show, and also the right range. For example, if this is 1.5 volt, this normal battery that you buy AA or AAA, so you adjust the range. What the range you're going to choose? Let me go back to the slide here. So if you want to measure 1.5 volt, so which range do you think you are going to use? No, I couldn't hear. 20. Well, you can use 20, of course, because to 1.5. But let's look at this one. What is 2,000 millivolts? 2 volt, right? That would be good. Then you will ask me, if I use 2,000 millivolts and 20, both are right. You can use even 200, because it's 200 is more than 1.5 volt. On the safe side. But the accuracy and the number of digits you are going to see on the screen will be rounded. Okay. If you want to 1.5, maybe the voltage of the battery that you are measuring is not exactly 1.5. Maybe it's 1.421. You will not get this one. You will not get this all precision. When you. So it's better we get closer to the range to have good precision of our measurement. But it's not wrong. So you will see you got like this one, 1.5001. Okay. That's how you measure the voltage you connected in parallel. That's a circuit here to measure the voltage across a light bulb. You see here, that's the voltage source E, and that's a resistance. I want to explain what's the resistance, what is the value of resistance, and you have a light bulb. If you want to measure the voltage across this light bulb, that's DMM to measure. You make sure this is the red one, and this is the common. And then you ask me why, and what's the difference? And if I flip the connection, something wrong will happen in the circuit. Let me answer this question. Number one, the important part that you should connect in parallel. That's a must. If you connect this red to this part and the common to this part, you will get positive reading. Example. If the voltage across the light bulb was let's say 5 volt, you read 5 volt. If you flip the red and the common, you will get negative 5 volt. Why? Because the current entering here, so it should be entering the positive. So that's where the current entering you should connect the red. And leaving should go to the car. Yes.
In the previous slide, when you talked about where to connect the different wires, also red is positive. Okay.
Yeah, red is positive, yes. And look at that here, this is common. The common always, that's where the current going in. And this one you want to go out. So that's how you measure the voltage across any element, and how you measure the voltage of a voltage source, battery, anything. Okay. And of course, when you go to the lab and use, it will be very simple. Measuring current, that's different. You don't connect DMM in parallel. You connect them in series. So that's here. If you have a circuit like that, let's say that you have, and you are connected to a light bulb, and we'll show you how we measure the voltage across the light bulb. But now, and let's say that you have some kind of resistance here to limit the current. So this is lamp, and this is the voltage source. And I want to measure the current. To measure the current, DMM has to be connected in series. Has to be connected in series. When you use DMM to measure voltage, has to be connected in parallel. Remember this rule. This is always the error that happens in the lab. Sometimes I want to measure current, I adjust the DMM on amp, and then I connect in parallel. Wrong. Something wrong will happen. Fuse will be blown if we're lucky, or something will be there. Will be ruined. So remember, when I want to measure the voltage, DMM is connected in parallel. To measure the current, DMM has to be connected in series. Well, here, how I can connect in series? First, you got to know the direction of the current. Obviously, the current will be going in this direction, right? What is important to know the direction of current? To connect the right polarity to get the positive value on the screen of DMM. So what you will do, I'm going to disconnect the circuit at any place. Let's say I'm going to disconnect here. Why? Because I want to connect the DMM in series. So you have to disconnect. And here you go. That's, oops. And that's DMM. I'm going to measure the amp. And has two wires. One connected to the common, and the one normal one I'm going to connect to. So since the current is going in this direction, the current has to go in the red, in the positive, and the common has to be the current coming out. So that's the way you are going to connect it. See, separate the circuit, disconnect the circuit, and insert it in series. Why? So the current can go through the ammeter, through the coil of the ammeter or the DMM to measure it. This is the right connection. So that if you look at the way how we'll do it, that's the battery positive and this is the negative. All right. And the positive, of course, the current will be C. That's the positive terminal of the battery. The current coming out the positive, it will go through the red. And then coming out from the common, going the light bulb. Then you read positive and connected in series, and the polarity, you have to pay attention of the polarity to get positive value. If you flip it, still connected in series, you will get the right value of the current, but just you will see the negative. So once you see the negative value of the amp, so said, oh, I flipped the connection, but you did the right connection in series. That's the meaning. In electric circuit, you will find a lot you are using switches to switch on, switch off. There are many types of switches. You think this maybe we have switched like this one on and off? Yes, on and off, but there are many types. I'm going to show you only 2 types, not to overwhelm you by the old type of switch. They are so important, and you can use them. You know, if you like, one time I can show you some different of switches. I don't know, like in my house, for example, the basement, I made like connection that when I go to the basement and I want to go to garage, so I have switch, so I switch on, it turn off in the end of the hallway where it's close to the garage, and I walk, and I want to turn off from the other switch, I turn off the setting. So it's like you can have 2 switches. I'm sure that you have this in the house, 2 switches. You can turn it on, turn off from either one. That will be very helpful. This kind of switch, not like this one, different. Let me show you. There is one here. We call it SPST, single pole, single throw. S means single, P means pole, and T throw. So this is the normal one. It's either on or either off, one position. This one. You have another switch, SPDT. As you see, it's a single pole, but it says double throw. What does it mean? You look at this switch here. It has 2 positions. When you switch, look at this first one. This one is either on or off, one. But this one, if you switch it, you may change from one to another position, and maybe one connected to one circuit and 2. Okay. And 2 connected to another circuit. So let's see how can you take advantage of this. And it would be interesting if we can get in the lab switch like this one is PDT, and you test by the DMM to when you switch it, you see which 2 are connected. It's very important. And we are going to learn that so you can design your circuit. Yes.
So when one is on, then 2 is off.
Yes. And when it turns on, so you can turn on and off between 2 circuits. And I'm going to show you one of the application. This one is normal on and off, just when you cut electric current or you make the current connect. So that's of course you are using SPST, single pole, single throw. It just you want to turn it on, turn off, like this one we have in the classroom. But and that's how you connect it. You get the battery, you have positive and negative, you connect it in series with the switch, with the light bulb or LED. So if you want to turn it on, turn it off, you know that's all connected in series. It doesn't matter which pole, it doesn't make any big difference. But when you are using the other PDT, that's different. Here you go. I'd like to show you this one, SPDT, how you can use this switch. So you got the switch here, that's position 1 and that's position 2. You got 2 light bulb, L1, L2. And you have 1 volt source. Let's say it's 6 volts, for example. So let's check what happens if it's connected here in one side. So the current will come from the positive. Well, let's see. It can go through L2. Why? If you try to go L2, it's open, and current cannot flow in open circuit. Can't. It's like water, in a pipe. The pipe has to be connected, or not, will not reach there. So nothing will go through L2. So let's continue. So we'll go through this line, go through L1. Because connected, go to the negative. It completes the circuit. So when at position 1, only lamp 1 will be on. Now let's see what happens if you flip the switch to position 2. So this one will be off. and this one connected. So when you go now, it will not go through L1. Why? Because it's just open. There's nothing here. Nothing. It's open. So it will go through L2, and then you can turn L2. So by this one switch, not two switch, one switch, when you flip it, you can turn on one light bulb or another one. Or maybe you don't have to have light bulb, of course. You can have, for example, fan, and you have a light bulb. And then you want to turn on this light bulb, or you on the fan. Yes. Oh, in this case, what do you think we'll do? You're an engineer. If you want to turn off both, what you'll do?
Take the battery out.
Pardon me?
Take the battery out.
Well, that's, yeah, but when you have circuits, let's say we're making using battery, but maybe you're doing work in the house. So yes.
Could you do it so it's not touching one and not touching two?
You can. It's all that's a single pole. You want to say something? You raised your hand. You didn't raise your hand?
I did it, but I'm
Oh, you got to say.
No, it-
Once you raise your hand,
It
that's
was
it.
already said.
Oh, you said okay. Yeah, it's very simple. What element you're going to add? Yes.
Switch.
Yes, you add the first type is single pole, single throw. You add in series. You see, you put here one switch, and you make it on your circuit operating. You go one or two. You want to turn off all of it? Just turn off. That's good also protection. Yeah. So, and there are many nice switches really. There is double pole, double throw with relays. You can do many things really like magic, with only switch. We have element fuse, and I'm sure that all of you are familiar with fuse. This is for protection. If how the fuse operate, this is of course the old type, but still used in many appliances, and even in car. In your car, you still have this type of fuse, maybe different shapes, the nice colorful one, but still working on the same principle. And the principle you have inside this glass wire, thin wire, designed in a way, if the current is exceeded, it will expand by the heat, and then will be disconnected, broken, and then disconnected to disconnect the circuit. So it's like a switch, but this switch operating on the high current. If the current exceeds the rated value of this wire will be overheated and melted. And when melted, broken, it's like switch will be off all the time. You cannot connect it on again. You have to replace it. Once this fuse is blown, you cannot replace it because the wire is broken. It's melted. So that's why protection for overload current. And that's what you have also inside your car. Maybe inside your car, find like fuses, a nice plastic cover, red and blue, and then you got two metal part here. But if you look inside, you will see they have wire. Maybe you cannot see, but there's wire. If they, some types they have like glass window, you can look at it. You can see this thin wire. And of course, they are different amp. Like you have 2 amp, 5 amp, 10 amp, 20 amp. What does it mean? 5 amp means if you exceed 5 amp, it will blow. Yeah, that's for protection. And sometimes you have like bays for it. Oh, I got it here. That's the picture. That's exactly like in your car. When you open the fuse of the car, that's the one. And this is the little fuse wire. Sometimes have bays, yes, in some appliances where you can replace the broken one. Of course, in the house, you'll find like a circuit breaker. That's kind of fuse also, but it's nice. Switch. My house in Cleveland was like an old one, like historical one. So I found that they have fuses. I don't have the picture here. It's like you unscrew it and screw it. I don't know if it's still sell it in Home Depot, but it has the same principle. So I replaced with the new one. The new one is nice. It depends on the. I think when the current go through and exceeded the rated value, the magnetic field will be exceeded and then will disconnect it. But it can be connected again. You don't have to replace it. It's like switch electromagnet. on and off, can be on and off, but it does not work on the same principle as fuses, that if the current exceeds the rated value, it will overheat it and melt. No, it will just increase the magnetic field and then it will be open. And then after the overcurrent is removed, you switch it back again, it works. We call it circuit breaker. If you open the one in your house, you see you have many switches, and each switch connected to some line. One protecting for appliances in the kitchen, one in the AC, one in the boiler, and so on. And you'll find some numbers and even written, you know, this is for the garden, that's for the, so each group of switches or circuit breaker protecting a specific instruments or devices.
So what should be, in example with the circuit breaker, which of these symbols is how you draw a circuit breaker?
That's the symbol here. That's,
All one
yeah,
symbol?
yeah. Just like circle open, yeah, can be open close. And this is, yes, that's it. And that's how to operate. It's like relay, you know. You can see in this one is connected, but when you have overcurrent, it will make the magnetic field strong. It will attract this piece of metal, so it will be open here. You are? Oh, okay. That's your first lecture?
Yes.
Okay. So that's how to operate the circuit breaker. You see, the one here on the left, that's the normal, when the current is normal. When the current, they design it in a way like a relay. So if the current exceed in the coil here, it will make the magnetic field stronger because the current is higher than the normal value. So it would attract this piece of metal. When it attracted down, so it will disconnect this part, this contact from this contact. Then you tell me, so what? Well, this is connected to the whole circuit. You have to imagine if you have a load here, or light bulb, you know, or anything like that. So when it's connected, there is no current there because the current exceeded the value. So till it go back again to normal, so it will lose the strong magnetic field in this one, and then when go back again connected, then the current will go through again. Okay, that's how it operates, like a relay. That's a circuit breaker. Yes.
Something happens, and then when you go back to the circuit breaker, it becomes loose.
Okay, you see, if it would be, it become loose because as this is a simple structure of it, but of course this one to go back, I didn't show even like there is kind of spring connecting these things. So for many times when it happened many times, so circuits, you got two cases. Sometimes you have very bad short circuit, high voltage, and maybe it will destroy the electromagnet. And this is like very rare to happen. But if it happened many times, short circuit, and this one attracted to the electromagnet many times, so the spring will lose its elasticity, so it will not be able to reconnect again. That's what happened. It happened, yes, in my house many times. Like if first of all, if it's a bad quality, the bad quality circuit breaker, the spring elasticity is not good because you can buy two springs. There is one that you can stretch it and go back again, you know, as normal, and there is some kind of spring that it's, if you stretch it like 10 times, it loses its elasticity to come back again. That's one. The other thing, if it's really was a huge circuit breaker, a huge overcurrent that it destroyed the electromagnet. But this is usually rare to happen for the excessive overcurrent. So most of the cases, bad spring many times or short circuit happen that it will lose the elasticity of the spring. So obviously we are talking a lot, about many terminology because this is the first course in electrical engineering, and it's important to know the basic elements before we start using formula and mathematical equation. It will be easy, but it's important to know the all physical aspects of electric circuits here. So resistance. I'm sure that you heard about resistance. So what's the resistance and why it happened? So we said that electric current, it's a flow of electrons. So imagine there are some kind of particles moving inside small tubes. So it depends on this tube. How wide this tube, how long they are going to travel, what is the material? Are they swimming in soft, medium, or harsh, or thick? So all the things affect the movement of electrons. And in general, when electrons move, they can collide. When they collide, they can lose most of their energy. And then when they lose the energy, will stop moving, so the current will stop or decrease. Not all of them, of course, will lose their energy, but some of them. So it depends how many electrons you will lose their energy. And accordingly, the current magnitude will decrease, because we know that the current depends on the number of electrons flowing in a conductor. And that's where the concept of resistance. So the resistance obviously is like something opposing the flow of electrons or minimizing the flow of electrons on a conductor. And we call this property resistance. And resistance, it looks like that. It's very beautiful, actually, when you see it in the lab, colorful. And we're going to learn how to find the value of the resistance using this color code. But that's the how it looks, most of resistance. And how you sketch it, that we have two symbols, This is the symbol we're going to use. But if you saw that in some textbook, in Europe they use it, in England they use this kind of resistance. So, but this is the one that most commonly used. And the resistance is measured in ohm. This is the unit, ohm. So what's ohm? We learn about voltage. We learn about current. So what's ohm? All right. The resistance, which are simply, you can measure it by the ratio of voltage over current. So if you have one voltage, 1 amp, the resistance will be equal 1 ohm. We're going to talk a lot about the ohm, but this is an Ohm's law. But just I just want to give you something fast to understand what's ohm. The opposite of resistance, conductance. So conductance, G is equal 1 over R. So if you have R 22 kilo ohm, 22,000 ohm, that's the resistance. So the opposite will be G equal 1 over 22 kilo ohm, and it will be micro Siemens. Siemens is the unit of conductance. So 1 Siemens is equal 1 over 1 ohm. We used before, in my days, we didn't have Siemens. It's a new unit for conductance. We used in my days mho. That's the opposite of ohm that we were using. But now they have Siemens. This one makes sense for me more, but that's that's what they are using now, Siemens.
So what does conductance?
It's the opposite of resistance. And what's the resistance? It's something opposing the flow of current. For example, since you ask, so I'll go to Ohm's law. Like, let's say you have a resistance, and you don't know how many ohms, and you put a meter to measure the current, and you put voltmeter to measure the voltage across. So let's say that you measure the voltage, you find that you have 20 voltage. And you measure the amp, you find it's 2 amp. So it means the resistance that you have here 20 divided by 2, 10 ohm. So you have resistance of 10 ohm, means resisting the flow of the current. Because obviously, the resistance affects the magnitude of current. If you have constant voltage, for example, this 120 voltage, it means you have 20 voltage here. Why it's 2 amp? Because the resistance that allow only 2 amp to flow. Just try to imagine the resistance is like restriction in a pipe. Like, let me give you this. I always like this example. If you have pipe connecting two tanks and you have two tanks, you can have restriction in this pipe. And of course, if you have the height of liquid here higher than this one, you have difference of potential energy. The current will flow on this restriction. It depends on the size of the restriction, the size of flow, right? So this restriction represents resistance. For example, maybe you will have 1 liter flowing every minute, maybe half liter every minute, or maybe 1/4 gallon every minute. So with the flow of water here or the liquid, it depends on the restriction. Even if you close it completely by faucet, nothing will go. That means resistance is infinity. So resistance here is like restriction in time. It does not allow all electrons to flow. And I will explain what affect the value of the resistance. G, it's the opposite. It allow. Okay, it's how you find this by dividing 1 over R. Like if you have R is equal 10 ohm, so the conductance will be equal 0.1. And let me just say something. We say that the resistance is equal voltage over current, or you can say the current is equal voltage over resistance, right? That's how you get the current. That's Ohm's law, by the way. So the current equal voltage divided by resistance give you the M. And you can say I is equal G times V. G, it allows. So if you do the same, I, in this example, I is equal voltage is equal 20 voltage divided by 10 ohm, you have 2 amp, right? If you are using this one, I is equal G, G is equal 0.1 times V is equal 20 voltage, equal to amp. Get the same. So that's the meaning of the resistance and the conductance. Yes. Oh, yes, it's the same thing. But it depends on what you are going to use. Like if you want the resistance here, you can write what's the value of the resistance found here. That's 10 ohm, right? So you write 10 ohm. I understand that this is the resistance, its value is 10 ohm, or you can put 0.1 Siemens. I understand that you are using the conductance. So the same symbol, because the same element, it's just a value. No, G equal 1 over R. Yes, it's the opposite of R. So G is here the equation. G is equal 1 over R. Yeah. And the relationship with voltage, you see, current is equal 1 over R times V. Current is equal G times V. Yes. And that's how I show here in this example. Here, the current is equal 20 divided by 10. I got 2 amp. Or I multiply 0.1 times 20. I got 2 amps. This or that. And that's the structure inside the resistance itself. It's made of carbon and in a way that it will resist the flow of electrons. And then you have insulation from outside, and you got these two connecting LEDs, so you can connect to the circuit. They are made of metal. Well, how to find the value of a resistor when you look at the resistor and you look at the color of the resistor. When you look at any resistor, you will see you have 1 band, 2 band, 3 bands, 4 bands. All right. So we are talking now about the common resistor. They have 4 bands. That's 1. That's 2, 3, 4. The fourth one, which is, we call it tolerance code, it doesn't have many colors. It's either gold or silver. Gold or silver. And it doesn't tell me about the value of the resistance, but it tells me about the tolerance. What does it mean? There is nothing is precise. So always there is kind of error. When I say this is 20 ohm, it doesn't mean 20 ohm. It could be plus or minus some error percentage. So if it's gold, it's 5%. If it's silver, it will be 10%. Yes.
How do you tell, when you look at a resistor, you can kind of turn it around.
Yes, you can turn it out.
Like-
Look at the gold and the silver, because the tolerance, it has only 2 colors, gold and silver. Make it to the right. That's it. Yes. And then start from the left. So when I look at the resistance, just I see what is the gold or the silver ring, and then I make it to the right. Okay, and then I'm in the right position. So only this 4th band, gold or silver, tell me about the tolerance. So for example, if you have resistance and you already 1 band, 2, 3, and then this one was like gold. So once you see it's gold, it means 5%. What does it mean? It means if you read the other 3 band, and I'm going to show you now, and you found out it's equal to 200 ohm using the first and the second and the third. You know it's 200 ohm. It does not mean it's when you measure by DMM, impossible to say it is equal to 100 ohm. It could be in the range between plus or minus 5%. So if this is R, ideal, so delta R, the error, could be 5%. So be 200 times 5 over 100. So what you'll get? 10 ohm, right? So you got tolerance 10 ohm. What does it mean? Subtract or add. So R, if you subtract, will be 200 minus 10. What you'll get? 190 ohm. And that's 1. That's the minimum. What's our maximum? If you add this tolerance, you will have 210 ohm. So when you measure the resistance, you should find the value of the resistance between 190 to 210. Could be 205, 209, 195, 192. All this would be in the range. So your resistance measurement should be greater than or equal to 190, less than 210. That means it gives you the range of the resistance. Yes.
I accidentally wrote 200 plus 100. instead of 200.
Oh, I'm sorry. That should be 10. Yeah. Yeah. So it's between 190 and 210. Any value between this. And we're going to check this in the lab. We'll get resistance and you get. How we find the value 200 ohm? That's the question. Using the code. There is equivalent digit for each color. You have black equal 0, brown equal 1, red equal 2, orange 3, yellow 4. By the way, I wrote here, but you can look at it. I'm kind of colorblind, Most males, they are inherit. That's colorblind. So I'm partially color, partially. Means like if I have the color, I can distinguish between them. But if you mix them in dots, this test, confused. I can tell. So now the first digit, second digit, number of 0. Let's see example. What does it mean? That's the first digit. That's the second digit according to color. And this, the third one, it tells you how many zeros. What does it mean? But you got to know, you got to have this paper with you that tell you about the equivalent digit for each color. Let's just have example here. That's the 3 bands. The first one is yellow. The first one is yellow. So what is yellow? You go back, yellow, it means 4, right? So you put 4. So yellow is equal 4. The second one, purple. That will be 1 where is the violet? Yeah, 7, right? Would be 7. And orange, you go to the table, orange, 3, right? 3. But the third one, zeros, you don't try 3, it means you have 3 zeros. So you have 4, 7, and the third one, it tells you the number of zeros, 3 zeros. So the resistance, you have it here, it's equal 47,000 ohm. Or you can write it 47 kilo ohm. That's the value. And the last one, gold, it means plus or minus 5%. So that will give you the percent. Well, in piece of paper that's your practice today, you're going to write your name, and make sure that you're going to give it to me. So just write it and give it to me your name, and then write IC in class practice number 2, and that's the yellow, purple, gold. I'm sorry, let me give you, that's not complete. I'll give you one. It has to have 3 things. I'll change this. Red. Green. Red. And this one, silver. And the question is, I want to find for me the range. R is greater than R minimum, less than R maximum. I want to find for me R minimum and R maximum for this resistor. Red, green, red. Yes. Yes. Okay, but remember, you have the code in front of you to the right here that give you the number: black 0, brown 1. Let me show you the example here for a while. This one. Okay.
No, that's still.
Yes. Red, green, red, silver. Yes. Okay. That's it. And you have the table. Not you just easy just put on. Did anybody inside sign the attendance sheet? Yeah. Is it?
And that's for my signature.
Yes. You can, yeah. Whoever done, it can leave. Did everybody submit the in-class practice one on the Dropbox?
Yeah, we gave it to
We
you.
gave it to you.
Oh, you give it to me? Okay.
Did you want us to give us to a drop?
Yeah, who didn't submit it to me, supposed to do it in the Dropbox.
Like on campus?
On campus, yes. On campus. Yeah, who did not submit it to me?
Oh. So if you don't hand it physically,
That's
do
it.
it on.
Okay.
Gotcha.
Because the first one, I understand, and you come to the one who passed. But after that, if it's that time, I'm just going to do that.
Okay. Thank you.